Somewhere beyond the last planet, beyond Pluto, beyond the reach of sunlight itself, a machine built in the 1970s is still sending us a signal. That signal is so faint by the time it reaches Earth that we need an antenna the size of a stadium just to hear it. It weighs less than a whisper, and it takes more than 22 hours to arrive, crossing a gulf so wide that the spacecraft sending it is now over 15 billion miles from the Sunday. The machine is called Voyager, and in the year 2012, it did something no object made by human hands had ever done. It reached the edge of the solar system. It crossed the invisible wall where the power of our star finally runs out and the rest of the galaxy begins. For 50 years, scientists had been drawing maps of that edge. They had the textbooks, they had the equations, they had the supercomputer models that told them exactly what the boundary of our home would look like, its shape, its temperature, the way the magnetic fields would bend, the moment everything would change. And then Voyager actually got there. The map was wrong. Not slightly wrong, not off by a rounding error. It was wrong about the shape of the edge, wrong about what was waiting on the other side, wrong about the one thing every scientist was most certain of. The bubble was the wrong shape, the boundary was in the wrong place. A great wave that every textbook drew at the front of our solar system turned out not to exist at all, and the single measurement everyone was certain would change at the crossing simply refused to change. The real boundary of the solar system turned out to be a place stranger than anyone had dared to imagine, and reaching it forced us to redraw the border of everything we call home, in a machine older than most of the people who would read the new map. Like and subscribe, and travel with us all the way to the edge of the known. On the longest journey in human history, settle in. We begin. The most important border crossing in human history happened in complete silence, and nobody noticed for almost a year. There was no alarm, no engineer leaping from a chair. When Voyager 1 finally slipped out of the sun's domain and into the space between the stars, the spacecraft itself didn't know it had happened. The scientists watching from Earth didn't know either. The news was already crawling home across the dark at the speed of light, and even at the speed of light, it would take most of a day to arrive. For more than 50 years, a physicist named Ed Stone had been waiting for this moment. He became the project scientist for Voyager in 1972, before the spacecraft had a name, before it had been built, when it was nothing but a proposal and an impossible idea. He would keep that job for half a century, and the thing the entire mission had been quietly racing toward came down to a single, almost absurdly humble number: the density of the space around the spacecraft. That sounds like nothing. It is everything. Inside the sun's territory, space is filled with a thin wind of charged particles streaming out from our star. Hot, fast, and faint. But the space between the stars is filled with something different. A colder, denser sea of particles left over from ancient dead suns. If Voyager ever crossed from one into the other, the density around it would jump. The one unambiguous signal that would tell us a thing built on Earth had finally left the bubble of its own star. Whole careers had been spent waiting for it. An entire field of science had been built around the question of where and when it would come. The instrument that should have measured that density directly had broken in 1980. 32 years before the spacecraft reached the boundary, Voyager was about to make the most anticipated measurement in the history of space exploration half-blind. So the team got clever. They used a different instrument, one designed to listen when a burst of energy from the sun rolls outward and slams into the gas around the spacecraft. It makes that gas ring like a struck bell. Voyager could hear that ringing, and the pitch of the ring depends on exactly one thing: how dense the gas is. Listen to the note, and you can calculate the number you cannot measure. In the spring of 2013, a shockwave from the sun finally reached Voyager and rang the space around it. The team listened. They did the math, and the density they calculated wasn't a little higher than the sun's territory. It was 40 times higher. Voyager was already on the other side. It had been for months. The instruments, working backward through the data, fixed the moment of crossing at August 25th, 2012. A date that will be remembered as long as there are humans to remember anything, the day a thing we built left home. But here is what almost nobody tells you about that triumphant moment. The crossing itself raised more questions than it answered. Because the way Voyager crossed, what the magnetic field did, what it didn't do, the strange foam it had to push through to get there, none of it matched the map. To understand just how wrong that map turned out to be, we have to go back to the beginning. Back to a once-in-a-lifetime accident of the heavens that made this whole journey possible in the first place. Once every 176 years, the outer planets line up. Not in a straight row. Nature is rarely that tidy, but every 176 years, Jupiter, Saturn, Uranus, and Neptune drift into an arrangement along one side of the Sun that makes something extraordinary possible. A single spacecraft, launched at exactly the right instant, could visit all four. It could use the gravity of each giant planet to fling itself toward the next, chaining one world to another, riding a cosmic current that nature only switches on twice every 3.5 centuries. A graduate student at NASA's Jet Propulsion Laboratory worked out the alignment in the mid-1960 seconds. The math was beautiful, and the timing was cruel. The window would open at the end of the 1970 seconds. Miss it, and the next chance wouldn't come until the middle of the 22nd century. Everyone alive to read the calculation would be long dead before the door opened again. Think about what that means. The last time this alignment had been usable, Thomas Jefferson was president. The next time after the 1970 seconds, no one watching the launch would live to see it. Humanity had exactly one shot, and it happened to fall inside the narrow handful of years when we had finally built rockets powerful enough to take it. So we took it. 2 spacecraft were built, twins, nearly identical, and given a deceptively modest name. Not Pioneer, not Explorer, Voyager, a word that promised distance. Voyager 2 launched first, on August 20th, 1977, but on a faster, steeper trajectory that would let it overtake its twin and reach Jupiter first. From the very start, the names were backwards, and the 2 ships were on 2 different destinies. One would become the great tourist of the outer planets, the only machine ever to visit all 4 giants. The other would become the runner, the one that would sacrifice everything else for speed, and one day become the most distant human object in existence. Neither of them was built to do what they ended up doing. Officially, the mission was a 4-year flight to Jupiter and Saturn. 4 years. That was the promise. Everything beyond that was unfunded, unplanned, almost unspeakable inside the budget meetings. The engineers built the spacecraft to survive the radiation of Jupiter and the long, cold cruise to Saturn. And then, officially, their job was done. They are now in their 48th year. The people who built these machines designed them to last 1,000 days and accidentally built something that would outlive its own creators. And to understand how a 1970 seconds machine could possibly still be alive in interstellar space, you have to understand what's actually inside it. Because by the standards of the device you're holding right now, Voyager should be impossible. Voyager has less computer memory than a musical greeting card. That is not an exaggeration for effect. The entire spacecraft, every system, every instrument, the brain that controls a billion-dollar mission at the edge of the solar system, runs on about 70 kilobytes of memory. The phone in your pocket has millions of times more. A single photograph you took this morning would not fit inside Voyager's mind. It would overflow it dozens of times over. This is a machine designed before the personal computer existed, before the internet, before the cell phone, the laptop, the video game console you grew up with. Its programmers wrote its code on paper. When something goes wrong 15 billion miles away, engineers have to dig through manuals that are older than most of the people now keeping the mission alive. Manuals written in a computer language almost no one is trained in anymore. The people who can still read that language are a vanishing few. Some of the original engineers have been called back from retirement to explain choices they made half a century ago, to translate the logic of a machine built by hands that are now old or already gone. Every year, the circle of human beings who truly understand how Voyager thinks grows a little smaller, and still the spacecraft answers when they call. A 1,970 seconds mind, fluent in a dialect of computing the world has almost entirely forgotten, holding a steady conversation across the largest gap any humans have ever bridged. And yet it works. Decade after decade, it works. Part of the secret is the power source. Voyager doesn't run on solar panels. Out where it's going, the sun is too faint to be useful, just another bright star in a black sky. Instead, each spacecraft carries a small block of plutonium. As the plutonium decays, it gives off heat, and that heat is turned into electricity. It is, in a very real sense, a tiny nuclear heart, and it has been beating without pause since 1977. But that heart is dying. The plutonium produces a little less power every single year, about 4 watts less every year, like clockwork. When Voyager launched, it had enough power to run all of its instruments at once. Today, it does not. The engineers have spent years playing a slow, agonizing chess game with physics, shutting off one system after another, trading capability for survival, keeping the most important instruments alive by sacrificing the rest. Heaters that keep the electronics from freezing in the interstellar cold have been switched off, and somehow the hardware has kept running at temperatures it was never rated to endure. Then there are the gold-plated dishes, the cameras, the magnetometers on a long boom, and one object bolted to the side of each spacecraft that has nothing to do with science at all. An actual phonograph record, plated in gold, sealed in an aluminum case, carrying a message to whoever, or whatever, might one day find it. We'll come back to that record, and to the haunting question of who it was really made for. But first, the twins had to survive the most dangerous thing in the solar system, the thing that would give them their speed, and very nearly kill them on the way, because to reach the edge, Voyager first had to fall toward a monster. You cannot reach the edge of the solar system by simply pointing a rocket at it and firing. The distances are too vast and the fuel required would be too enormous. No rocket humanity has ever built carries enough propellant to push a spacecraft all the way to interstellar space under its own power. Voyager doesn't have a giant engine. It has barely any engine at all. So how does a machine that ran out of meaningful thrust within hours of launch end up moving faster than any object in history? It steals. The trick is called a gravity assist. And the first time you understand it, it sounds like cheating the universe. As Voyager fell toward Jupiter, the planet's immense gravity grabbed it and whipped it around in a tight curve, flinging it back out the other side far faster than it came in. The spacecraft didn't burn a drop of fuel to gain that speed. It simply borrowed it, taking a microscopic sip of Jupiter's own orbital motion and converting it into velocity. Picture a tiny ball thrown gently at a speeding train. If you throw it at the front of the train and it bounces off, it comes back screaming, carrying away a fraction of the train's enormous momentum. Voyager did exactly that with a planet 300 times the mass of Earth. Jupiter lost an immeasurably small amount of its speed, so small it can never be detected. And Voyager gained the kick of a lifetime. This is the real reason the planetary alignment mattered so much. Voyager 2 could chain these maneuvers together, fall toward Jupiter and get flung to Saturn, fall toward Saturn and get flung to Uranus, fall toward Uranus and get flung to Neptune. Each giant handed the spacecraft to the next like runners passing a baton. And at every handoff, the spacecraft got faster. Without the gravity of those 4 worlds, the journey would have taken not decades but centuries. But there was a price, and the price was terror. To steal Jupiter's speed, Voyager had to fly close enough to plunge through the most lethal radiation field in the solar system. Jupiter is wrapped in a belt of charged particles so intense that the dose Voyager absorbed in a single pass was 1,000 times what would kill a human being. The engineers had hardened the spacecraft as much as they could, wrapping its most delicate parts. But no one was certain it would survive. They were sending their fragile machine straight into the lion's mouth. And the lion was the largest planet in the solar system. Voyager went in, and what it saw when it got there rewrote the textbooks for the first of many times. Because the moons of Jupiter were supposed to be dead, frozen rock, they were anything but. Everyone knew the moons of the outer solar system were dead. It was obvious. It was settled. Out there, so far from the sun's warmth, the small moons of the giant planets had to be frozen, cratered, geologically lifeless balls of rock and ice. Miniature versions of our own dead moon, scarred by ancient impacts and otherwise unchanged for billions of years. There was no reason to expect anything else. The textbooks said so. The models said so. Then Voyager 1 sent back a photograph of a moon called Io, and a young engineer named Linda Morabito, working on navigation images, noticed something rising off the edge of it. A strange, faint, umbrella-shaped cloud hanging above the moon's horizon. It was a volcano, an erupting volcano, throwing a plume of material hundreds of kilometers up into space. This was impossible according to everything anyone believed. Io is a small moon, far from the sun, the kind of world that should have frozen solid and gone quiet eons ago. Instead, it was the most volcanically active body in the entire solar system. More active than Earth, its surface a hellscape of erupting calderas and rivers of molten sulfur, constantly resurfacing itself, glowing with internal heat. Voyager had caught not one eruption but many, a moon on fire, where there was supposed to be only ice. The reason turned out to be Jupiter itself. The giant planet's gravity squeezes and stretches Io as it orbits, kneading the moon like a stress ball. And that constant flexing heats its interior until it boils. It was a mechanism scientists had barely considered, and Voyager had just shown it operating on a planetary scale. And Io was only the beginning. The spacecraft turned its cameras on the other moons and kept breaking the map, Europa, wrapped in a shell of smooth, cracked ice that looked unsettlingly like a frozen ocean, and might be hiding a real one, liquid water beneath the crust, the most promising place to look for life beyond Earth. Ganymede, larger than the planet Mercury. Callisto, battered beyond recognition. 4 little worlds, each one stranger than the last, none of them matching what we had drawn. And above them all turned the great red spot. A single storm larger than the entire Earth. A hurricane that has been raging in Jupiter's clouds for centuries without end. Voyager watched it spin in detail no telescope had ever managed, watched smaller storms get caught and swallowed at its edges, and revealed it as a living, churning system of almost incomprehensible scale and violence. The giant planet and its moons together were not the quiet, finished corner of the solar system anyone had expected. They were a roiling miniature kingdom, more active, more violent, and more alive with process than the textbooks had dared to predict. Voyager had been at its job for only a couple of years, and it had already proven a humbling lesson. The universe is under no obligation to look like our diagrams of it. Out here, the real thing was always wilder than the map. That lesson was about to repeat at the next world, and at Saturn, Voyager 1 would make a choice that sealed its destiny forever, trading the rest of the planets for a one-way ticket to the edge. At Saturn, Voyager 1 made a decision that ended its tour of the planets and began its journey out of the solar system. The rings came first. For centuries, humanity had seen Saturn's rings as a few smooth bands through telescopes. Voyager flew close and revealed the truth. Not a few rings, but thousands of them. An impossibly intricate structure of ringlets within ringlets, braided and kinked and shepherded by tiny moons, a system so complex that scientists are still arguing about how it stays the way it is. There were spokes, dark radial features sweeping across the rings that no model had predicted. And that took decades to even begin to explain. Once again, the close-up reality made the textbook diagram look like a child's sketch. But the real prize at Saturn wasn't the rings. It was a moon called Titan. Titan is the second largest moon in the solar system, and it is the only moon with a thick atmosphere. A dense, hazy, orange shroud that completely hides its surface. To the scientists of the Voyager mission, Titan was irresistible. An entire world wrapped in air, possibly with weather, possibly with liquid on its surface, possibly with a chemistry echoing the young Earth. They had to know what was under that haze. And here was the dilemma. To fly close enough to study Titan properly, Voyager 1 would have to pass beneath it on a path that flung the spacecraft sharply upward, out of the flat plane where all the planets orbit, angling it north, away from everything else. Take that path, and Voyager 1 could never visit Uranus or Neptune. The Titan flyby would be the last planet it ever saw. Its grand tour would be over, and it would spend the rest of eternity climbing out of the solar system at a steep angle into the dark. They chose Titan. It was a bet on the unknown. And in one sense, it didn't even pay off the way they hoped. Titan's haze was too thick, and Voyager's cameras couldn't see the surface at all. It would take another mission, decades later, to find what Titan was hiding. Lakes and seas of liquid methane. The only other place in the solar system with stable liquid on its surface. Voyager had pointed the way without being able to look. But that fateful slingshot did something else. It threw Voyager 1 onto the fastest path out of the solar system of any object ever launched, and it aimed the spacecraft toward the edge. The choice that cost it the outer planets is the exact reason it would become the first human-made object to cross into interstellar space. Voyager 1 gave up the tour to become the pioneer. Its twin, however, stayed the course. Voyager 2 kept to the plane of the planets and pressed on toward two worlds no spacecraft had ever seen, or has ever seen since. To this day, only one spacecraft in history has ever visited Uranus and Neptune. It was Voyager 2, and it will likely hold that record for the rest of your life. By the time Voyager 2 reached Uranus in 1986, it was already a battle-scarred veteran. 9 years into a 4-year mission, its instruments aging, its signal growing fainter with every passing year. And what it found at Uranus was a planet that made no sense. Uranus is tipped over. Every other planet spins more or less upright as it circles the Sun, like a top. Uranus lies on its side, rolling around its orbit like a ball, its poles pointing nearly at the sunday. Something catastrophic must have knocked it over in the distant past. A collision with a world-sized object, most likely. And the result is the most extreme seasons in the solar system. Each pole spending decades in continuous sunlight, then decades in total darkness. From a distance, Voyager saw an almost featureless blue-green orb, eerily calm, hiding its violence beneath a smooth haze. Then came Neptune in 1989, the last planet, the final encounter, 12 years after launch and billions of miles from home. And Neptune, the most distant giant, was supposed to be the calmest and coldest of all. Instead, Voyager found the windiest planet in the solar system, with storms tearing through its atmosphere at over 1,000 miles per hour, and a vast dark storm the size of Earth churning in its clouds. So far from the sun's heat, there should not have been enough energy to drive weather like that. The map said quiet. The reality screamed. And then Voyager 2 saved its strangest discovery for last. Neptune has a large moon called Triton, and Voyager flew close. Triton orbits backward, circling its planet in the opposite direction to Neptune's spin. a sign that it was probably captured from somewhere else, a wanderer adopted by the giant. Its surface was a bizarre, pinkish landscape unlike anything else seen before. And there, on this frozen moon at the very edge of the planetary solar system, where the temperature drops to among the coldest ever measured anywhere, Voyager spotted dark plumes rising from the surface. Geysers, active eruptions of nitrogen, venting into the thin sky on a world so cold it should have been utterly, permanently dead. The same impossible lesson learned at the opposite end of the solar system. Even here, even in the deep freeze, the worlds were alive with processes we had not imagined. Voyager 2 had visited every giant planet in our system and found at every single one that the truth was stranger than the map. Neptune was the end of the planets. But it was not the end of the mission. As Voyager 2 climbed away from Neptune, and as Voyager 1 raced outward in the north, the cameras would soon take one final photograph. And it would change how our entire species sees itself. On Valentine's Day, 1990, Voyager 1 turned around and took a picture of home. It is, by any reasonable measure, the most important photograph ever taken. The spacecraft was about 6 billion kilometers from Earth. Past the orbit of Neptune, its planetary work long finished, its cameras about to be switched off forever to save power. And one man fought for years to use them one last time before they went dark. His name was Carl Sagan, and he wanted Voyager to turn its camera back toward the sun and photograph the Earth from the greatest distance any spacecraft had ever achieved. There was resistance. Pointing the camera so close to the sun risked damaging it, and from that distance, Earth would be almost nothing. There was no scientific value in the image, no data to be gained, but Sagan understood something the instruments couldn't measure. He understood what it would mean for humanity to see itself from the outside. So, Voyager turned, and it took the picture, and in that picture, the Earth, everything we have ever known, every person who has ever lived, every empire, every war, every love story, the entire stage of human history, is less than a single pixel. A tiny point of pale light, caught almost by accident in a stray beam of scattered sunlight. You can barely find it. You have to be told where to look. Sagan called it the pale blue dot, and the words he wrote about it have never been equaled. He looked at that speck of light suspended in a sunbeam and saw the whole of human existence reduced to its true cosmic scale. Everyone you love, everyone you have ever heard of, every human being who ever was, living out their lives on a mote of dust, hanging in a vast and indifferent dark, and the pale blue dot was only one frame of something larger. On that same day, Voyager turned and photographed not just the Earth, but the whole solar system, capturing a series of portraits of 6 of the planets strung out across the blackness. The first and only time any spacecraft has ever turned around at such a distance to take a family portrait of the worlds it left behind. Each planet, including our own, was nothing more than a tiny point of light, scattered like dust across the dark. The entire solar system that had taken Voyager 12 years to cross fit into a handful of grainy frames, every world reduced to a speck you could blot out with a fingertip. It is impossible to look at that image honestly and feel the same about our quarrels, our borders, our certainty that we are the center of things. From 6 billion kilometers away, the most powerful nations and the smallest lives occupy the very same pixel. We are all, every one of us, riding the same fragile speck through the same enormous night. That photograph was a gift from a machine that was about to fall silent as a camera and become something else entirely, an explorer of the dark between the stars. Voyager had shown us how small we are. Now it was going to show us how little we actually understood about the edge of our own home. But it carried one more thing into that dark. Not a picture sent back to us. A message sent forward to someone who may not exist yet, and may never exist at all. Bolted to the side of each Voyager spacecraft is a golden record, and it may be the longest-lasting object our species ever creates. It is a real phonograph record, 12 inches across, plated in gold, and sealed in an aluminum cover. And it was designed to last not for years, not for centuries, but for 1 billion years or more, long after every building on Earth has crumbled, long after the continents have rearranged themselves, possibly long after humanity itself is gone. Out in the vacuum of interstellar space, where there is no air to corrode it and almost nothing to strike it, the record could survive, essentially unchanged, for a span of time that makes all of recorded history look like a single breath. Carl Sagan led the small team that decided what to put on it, and they were trying to answer an unanswerable question. If this is the one artifact of humanity that outlives everything else, if this is the message in a bottle thrown into the cosmic ocean, how do you introduce an entire species to a stranger you will never meet, who may not share a single thing in common with you, not even the senses you use to perceive the world? They did their best. The record holds the sounds of Earth, wind and thunder and rain, the songs of birds and the eerie calls of whales, a human heartbeat, a mother's first words to her newborn child, laughter. It holds greetings spoken in 55 languages, ancient and modern. It holds 90 minutes of music chosen to represent all of human culture. Bach and Beethoven, a Peruvian wedding song, Indian raga, and Chuck Berry's rock and roll sent rolling into the galaxy at the speed of a spacecraft. And it holds over 100 encoded images. A human face, a fetus, the structure of our DNA, the planets of our solar system, a child, a sunset. On the cover, etched in symbols, are instructions for how to play it, and a map, not of streets or countries, but of pulsars, the spinning cosmic lighthouses whose precise rhythms could let a finder triangulate exactly where and when this record was made and launched. Think about the strange genius of that map. Pulsars spin with such fantastically regular rhythms that each one is like a unique clock ticking somewhere in the galaxy. By marking our sun's position relative to a handful of them, the record's makers drew an address that depends on no language, no number system, and no shared assumption. An address readable, in principle, by a mind that shares nothing with us but physics. And because pulsars slow at known rates, the same map quietly encodes a date, not just where we are, but when we threw the bottle into the sea. It may be the most carefully addressed letter ever written, sent to a recipient whose existence we cannot even confirm. And here is the haunting truth at the center of it all. Voyager is moving so slowly against the scale of the galaxy that it will not come close to another star for tens of thousands of years. The odds that anyone will ever find the record, ever decode it, ever hear a human heartbeat or a child's laughter are so small they can barely be written down. Some say the golden record was never truly a message to the stars at all. It was a message to ourselves, a portrait of who we hope to be, assembled by people standing at the edge of the unknown, choosing in that moment to send out not our weapons or our fears, but our music and our voices and our love. We launched the best of ourselves into the dark, on the faint chance that the dark was listening. Voyager carried that message past every planet and out toward the boundary of the solar system itself, moving faster than anything our species had ever flung away from the Sunday. And to understand everything that happened next, you first have to feel just how fast and how far that really is. Voyager is the fastest thing our species has ever sent away from the sun, and the numbers behind that sentence are almost impossible to feel. Right now, Voyager 1 is racing away from the sun at about 17 kilometers every second. Not every hour, every second. In the few moments it takes to read this sentence aloud, it has already traveled farther than the length of a large city. It covers more than 1 million kilometers a day, every day, and it has done so without a single pause since the 1,970 seconds. The gap between the Earth and the Moon, the same gap that took the Apollo astronauts 3 days to cross. Voyager now crosses in about 6 hours. It earned that speed not from an engine, but from the giants. Every gravity assist, every slingshot past Jupiter and Saturn added another permanent burst of velocity. And because there is nothing in deep space to slow it down, no air, no friction, almost nothing to strike, that speed is now essentially forever. The engine died decades ago. The motion never will. Voyager will still be moving at very nearly this same tremendous speed long after our sun itself has died. And yet, against the scale of the journey it is on, even this looks like standing still. Consider the light. Sunlight reaches the Earth in about 8 minutes. To reach Voyager, that same sunlight now needs more than 22 hours. The spacecraft is so far away that a beam of light, the fastest thing in the entire universe, takes nearly a full day to get there. When we send Voyager a command, we then wait the better part of 2 days just to learn whether it worked. A day and a half for our question and its answer to make the round trip across the void. Here is the comparison that truly breaks the mind. Voyager has been flying at over 1 million kilometers a day for nearly half a century, and in all that time, it has covered only about 1/400th of a single light year. The nearest star to our sun is more than 4 light years away, the fastest object in human history, given 50 years of relentless, unbroken flight, has crossed barely the faintest sliver of the distance to even the closest neighboring star. That is the paradox of deep space. Voyager is unimaginably fast, and the universe is unimaginably large, and the second fact wins, completely, every single time. The very speed that makes Voyager the most distant thing we have ever built is the same speed that reveals just how staggeringly far away everything else really is. And it was out there, at the very edge of that staggering distance, after decades of this silent, million-miles-a-day flight, that the real journey of discovery began, and that the map we trusted began to fall apart. Here is a question that sounds simple and isn't. Where does the solar system end? Most people would say Pluto, or maybe the last planet, Neptune, but those are just the worlds closest in. The sun's true reach extends almost unimaginably farther, and the edge that Voyager was racing toward is not made of rock or ice at all. It's made of wind. The sun is not a quiet ball of light. It is a roaring furnace that blows a constant gale of charged particles out into space in every direction at over 1 million miles an hour. This is the solar wind, and it never stops. It streams off the sun and rushes outward, past Mercury, past Earth, past the giant planets, carving out an enormous bubble in the gas that fills the space between the stars. It's called the heliosphere, the true domain of our Sunday, and everything inside it, including you, is technically inside the sun's atmosphere. No matter how far from the sun you are, the heliosphere is staggeringly large. It is so wide that even Voyager, the fastest object we have ever launched, moving at more than 10 miles every second, needed 35 years to reach its outer wall. To cross our sun's bubble took a machine traveling fast enough to get from New York to Los Angeles in under 4 minutes, more than 3 decades of continuous flight. And the edge of that bubble, the place where the solar wind finally loses its battle against the gas of the galaxy and can push no farther. That is the real boundary of the solar system. That is the edge, not a line on a map between 2 planets, but a vast, invisible membrane wrapped around our entire star and everything that orbits it, holding back the rest of the Milky Way. Beyond that membrane lies true interstellar space, the medium between the stars, filled with the thin remnants of ancient suns that exploded long before our own was born. No human-made object had ever touched it. Everything we are, everything we have ever sent anywhere, had spent its entire existence inside the warm bubble of our own star. For decades, scientists had built increasingly elaborate models of what this boundary must look like. They knew the bubble had to have layers. They predicted there would be a place where the solar wind suddenly slowed, then a turbulent zone, then a final skin where it met the galaxy. They drew it carefully. They calculated its distance, its shape, its temperature, the behavior of the magnetic fields woven through it. By the time Voyager approached, the textbooks contained a confident, detailed map of the edge of the solar system. The only problem was that no one had ever actually been there. Every line on that map was a prediction. And predictions, as Voyager had already proven at Io, at Titan, at Triton, have a way of shattering when reality finally arrives. Voyager was about to test the map directly, with its own body crossing the boundary in real time, and the very first layer it reached was already in the wrong place. Before we follow Voyager across the edge, you have to understand exactly how confident the scientists were, because the confidence is what makes the story. This was not a vague guess. The boundary of the solar system was one of the most heavily modeled regions in all of space physics. Researchers had spent careers on it. They had the equations that govern how a stellar wind carves a bubble in interstellar gas. They had supercomputer simulations that rendered the heliosphere in 3 dimensions, color-coded and rotating, predicting every feature Voyager should encounter and the order it should meet them in. The map said this. First, far out, the solar wind would hit a kind of cosmic sound barrier and abruptly slow down, a feature called the termination shock. There, the wind, which had been screaming outward faster than any wave could travel through it, would pile up and break hard. And all that lost energy would turn into heat. The models were specific. The region just past the shock should be searing hot, the protons there heated to enormous temperatures by the violence of the slowdown. Then, the map said, Voyager would enter a relatively orderly outer region, the heliosheath, where the slowed solar wind would drift toward the boundary. The magnetic field carried by that wind would be smooth and well-behaved, bending in graceful curves. And finally, at the true edge, the heliopause, the most important prediction of all. As Voyager crossed from the Sun's domain into the galaxies, the direction of the magnetic field would change. It had to. Inside the bubble, the field is the Sun's, wound up by the Sun's rotation. Outside, the field belongs to the galaxy, pointing a different way. So, at the crossing, the compass should swing, the magnetic field should rotate to a new direction, and that rotation would be the unmistakable signature, the final proof that Voyager had truly left home. A smooth, orderly outer region, a magnetic field that turns at the boundary. 3 clean predictions, drawn with confidence, taught to students, printed in the textbooks. Voyager checked all 3. It got all 3 wrong. The protons weren't hot, the outer region wasn't smooth, and the magnetic field, the one prediction everyone was most certain of, the signature they were waiting for, did something that, more than a decade later, scientists are still struggling to fully explain. One by one, Voyager reached the features on the map, and one by one, it found that reality had not read the textbook. Let's follow it across, in the order it actually happened, starting with the cosmic sound barrier that turned out to be in the wrong place. In December 2004, after 27 years of flight, Voyager 1 hit the first wall, and immediately, the numbers didn't match. The termination shock is where the solar wind slams on the brakes. For the entire mission, the wind rushing past Voyager had been supersonic, faster than any disturbance could ripple through it. Then, suddenly, the spacecraft's instruments registered the wind, collapsing in speed and the magnetic field strengthening as everything piled up. Voyager 1 had crossed the termination shock at about 94 times the distance from the Earth to the Sunday, a distance so vast that light itself, the fastest thing in existence, needs 13 hours to cross it. That much, roughly, The map had gotten right, but two things were already wrong. The first was the heat. The models had been emphatic. When the supersonic wind crashed and slowed, all that lost motion should convert into temperature, heating the protons in the wind to millions of degrees. Voyager arrived, measured the temperature, and found the region far cooler than predicted. The energy of the slowdown had gone somewhere, but not into the heat scientists expected. It had been siphoned off into a smaller population of strange, energetic particles, in a process the simple map hadn't accounted for. The first feature on the chart, and the temperature was already off. But the second problem was the one that truly cracked the map open, and it didn't fully reveal itself until Voyager 2 arrived at the shock from a different direction. Voyager 2 reached the termination shock in August 2007, and it crossed at about 84 times the Earth-Sun distance. That is roughly 10 times the Earth-Sun distance closer than where Voyager 1 had crossed. Billions upon billions of kilometers closer. Sit with that. The two spacecraft were traveling outward in different directions. Voyager 1 angled up toward the north, Voyager 2 down toward the south. If the heliosphere were the neat, round bubble the textbooks drew, both spacecraft should have hit the shock at nearly the same distance. They didn't. The southern edge was pushed in, dramatically closer than the northern edge. The bubble wasn't a sphere. It was lopsided, dented, squashed in on one side like a ball someone had leaned on. Something was pressing on the heliosphere from outside, deforming the entire boundary of the solar system. And the prime suspect was a force the simple maps had badly underestimated. The magnetic field of interstellar space itself, pushing back against our sun's bubble and crushing it out of shape. The very first measurement of the edge had already revealed that the solar system is not the tidy sphere of the diagrams. And Voyager hadn't even reached the strangest part yet, because as it pushed beyond the shock, the very wind that had carried it for its entire life began to do something that wasn't supposed to be possible. It began to stop. For its entire life, Voyager had been riding a wind, and then, far out in the dark, the wind simply died. The solar wind had been the spacecraft's constant companion since the day it launched. The endless gale of charged particles streaming out from the sun in every direction, always rushing outward, always faster than Voyager itself. That wind was not a detail. It was the very thing that blows the bubble Voyager lived inside, the breath of the sun that holds back the galaxy. For more than 30 years, every instrument confirmed it. The wind at Voyager's back, pouring outward, hour after hour, year after year. Past the termination shock, scientists expected that wind to keep flowing outward, only slower, gradually easing off as it neared the final boundary still far ahead. The map showed a steady, fading outward current, all the way to the edge. Instead, around the year 2010, Voyager 1 measured the outward speed of the solar wind and found it had dropped all the way to zero. The wind had stopped. In the direction pointing straight away from the sun, it was no longer moving past the spacecraft at all. Voyager had drifted into a strange, still region near the edge of the solar system, a kind of cosmic doldrums, where the great outward current that had carried it its whole life finally ran out of push and went calm. This was not on the map. The models had the wind slowing, yes, but not stopping dead. Not here, not this far before the true boundary. And the more carefully the team looked, the more they realized the wind hadn't simply died. It had turned. The flow that could no longer push straight outward had begun to slide sideways instead, deflecting along the inside of the boundary the way water spreads sideways when it strikes a wall, bending to run back down the long flanks of the heliosphere. Voyager had found the exact place where the sun's exhale finally exhausts itself and curls away. It is a quietly staggering thing to picture. A wind that fills a bubble larger than the orbits of all the planets. A wind that has blown without pause for the entire history of the solar system. has an end, a place where it slows, stalls, and turns aside. And the only reason we know that place exists, the only reason we know where it is and what it does, is that a single machine rode the wind all the way to the spot where it died and felt it go still. The very first measurements past the shock had already shown that the outer reaches of the sun's domain were nothing like the calm, orderly approach the diagrams had drawn. And the deeper Voyager went, the more even the shape of the bubble itself dissolved into mystery. The discovery that the heliosphere is lopsided did something profound. It turned the edge of the solar system from a fixed line into a living, shifting thing. Voyager 2 didn't cross the termination shock once. It crossed it 5 times in a matter of days. The boundary swept back and forth across the spacecraft, surging outward and retreating inward like a tide. This is not a wall standing still in space. It is a membrane that flexes and ripples, pushed around by the changing breath of the Sunday. When the sun is more active and blows harder, the whole bubble inflates and the edge moves outward. When the sun quiets, the bubble shrinks and the edge falls back inward, by distances larger than the entire orbit of the outer planets. The edge of the solar system, in other words, breathes. It is not a place you can mark once on a map and trust forever. It moves, by billions of kilometers, on the rhythm of the sun's 11-year cycle of activity. The very idea of a single, fixed boundary, the thing every textbook diagram implied, was an illusion, and the shape was stranger than just dented. As the data came in from both spacecraft, scientists realized they could no longer even agree on what the heliosphere looks like. For decades, the standard picture had been comfortable and intuitive. A comet shape, a rounded nose on the front, where the sun plows forward through the galaxy, trailing a long tail behind. Like the wake of a boat. It made sense. It was easy to draw. The Voyager data, combined with other observations, began to break even that. Some researchers proposed the heliosphere has almost no tail at all, that instead of a comet, it's shaped more like a croissant, 2 great lobes curving forward, squeezed by the interstellar magnetic field into a form no one had drawn. Others argued for still different shapes. The debate is not settled even now. We have sent 2 spacecraft physically across the boundary of our own solar system, and we still cannot say with confidence what shape it is. Think about how humbling that is. We have detailed maps of galaxies millions of light years away. We can describe the first moments after the birth of the universe, and the actual shape of the bubble we live inside. Our own cosmic neighborhood, the boundary of our home, remains an open question, argued over in scientific papers, because the only 2 probes that have ever touched it sent back data that refused to fit any of the simple pictures. Voyager kept pushing outward through this flexing, lopsided, ambiguous region toward the true edge. And the more it learned, the more even the basic outline of our solar system slid into doubt. There was, in fact, one more feature of that outline that the old map had always drawn with total confidence. Far out at the front of our moving bubble, a great wave. And it turned out the wave was never there. For decades, every textbook drawing of the solar system's edge showed a great wave standing out in front of it. And one of the quiet shocks of the Voyager era was learning that the wave does not exist. The idea was simple and intuitive. Our entire solar system is not sitting still. The sun, dragging its vast bubble of wind and every planet along with it, is ploughing through the gas of the galaxy at tens of thousands of miles per hour. And when something moves through a medium that fast, it pushes a wave ahead of itself. The way a boat shoves a wave of water in front of its bow, or a supersonic jet cracks the air into a sonic boom. So the maps drew exactly that. A bow shock at the leading edge of the heliosphere, a standing shockwave out in front, where our racing bubble slammed into the gas between the stars. It was on every diagram. It was taught as settled fact. Then the measurements came in, and the wave dissolved. Part of the key was the strength of the magnetic field in the gas just beyond our solar system, something Voyager itself helped pin down once it finally crossed into interstellar space and could feel that field directly. Combined with better measurements of how fast the sun is actually moving relative to the local gas, the picture changed completely. It turned out that the heliosphere is drifting through the surrounding medium more slowly and through a more strongly magnetized gas than anyone had assumed. And that combination is too gentle to crack a true shock into existence. Instead of a violent bow shock, our solar system pushes only a soft swell ahead of itself. A bow wave, like the smooth mound of water that builds in front of a slow-moving boat, rather than the hard, breaking wake of a speedboat. The difference sounds technical. It isn't. It means the entire leading face of our solar system, the part that meets the rest of the galaxy head-on, is a calmer and gentler place than the textbooks had insisted for generations. A dramatic feature that had appeared in every drawing of our cosmic home simply had to be erased. It is one more entry in the same humbling ledger. We had drawn the front of the solar system. We had drawn its sides. We had drawn the smooth field within it. And one by one, as the real data arrived, each confident line had to be redrawn or rubbed out entirely. And the surprises about the shape and the front of the edge were only the beginning, because as Voyager pushed deeper into the heliosheath, the very zone the map had promised would be smooth and orderly. It found something the models had completely missed. The sun's magnetic field, out here at the edge, wasn't smooth at all. It had broken apart into a froth of giant bubbles. In 2011, scientists announced something about the edge of the solar system that nobody had predicted and almost no one had even imagined. Out there, near the boundary, the sun's magnetic field isn't a set of smooth, sweeping lines. It's foam. To understand why this was such a shock, picture how the sun's magnetic field reaches the edge. The sun spins, and as it spins, it winds its magnetic field outward into an enormous spiral, like water spraying from a rotating sprinkler. By the time that field reaches the boundary of the heliosphere, billions of kilometers out, it has folded back on itself again and again, packing layers of magnetic field pointing in opposite directions close together. The old map assumed those layers would stay relatively organized. The new analysis of Voyager's data, modeled by physicists studying how magnetic fields behave when they're crushed together, revealed something far wilder. Where those opposing field lines press against each other, they snap and reconnect, breaking up into a vast sea of self-contained magnetic bubbles, a frothing, churning region of magnetic structures, each one enormous, roughly 100 million miles across. That's larger than the distance from the Earth to the Sunday. Single bubbles in this foam are wider than the orbit of our own planet. Voyager wasn't gliding through a calm, orderly outer layer of the sun's field. The way the textbook promised, it was swimming through a turbulent froth of colossal magnetic bubbles, disconnected and reconnected, a structure with no place at all in the old picture of the edge. And this wasn't just a curiosity, it changed our understanding of one of the most important questions in all of space science. How does the galaxy get in? Beyond the heliosphere, interstellar space is filled with cosmic rays, particles accelerated to ferocious energies by distant exploding stars blasting through the galaxy. The heliosphere is our shield against them. The sun's bubble deflects most of these cosmic rays, and that shielding is part of what makes a calm enough environment for life to exist. For decades, scientists assumed the edge worked like a smooth barrier, gradually filtering those particles out. But if the edge is a sea of magnetic foam, the rules change completely. The bubbles might trap some cosmic rays and channel others through, making the boundary less like a solid wall and more like a porous membrane, full of gaps and pockets and connections. Voyager had revealed that the very shield protecting our solar system from the radiation of the galaxy works in a way no one had drawn, with consequences we are still working out. And that shield is not an abstraction. The heliosphere, this lopsided, foaming, breathing bubble, is the reason the inner solar system is bathed in far fewer cosmic rays than the raw galaxy would otherwise deliver. Those rays can shatter living cells and break apart the delicate molecules that life depends on. The bubble our sun blows is, in a very real sense, part of what makes a calm enough harbour for life to have taken hold on Earth at all. So when Voyager discovered that the wall of that harbour is full of magnetic froth and porous gaps, it wasn't merely correcting a diagram, it was teaching us something about the conditions that allowed us to exist in the first place, and about how those conditions might rise and fall as the sun's protective bubble swells and shrinks across the long ages. The spacecraft pushed on through the foam, its power dwindling, its signal fading, edging closer to the true boundary. And as it approached, it entered one final, unexpected region, a place the scientists, scrambling to name something they hadn't predicted. In the middle of 2012, Voyager 1's instruments went haywire in a way that nearly fooled the entire team into announcing the wrong thing. Almost overnight, 2 of the spacecraft's readings flipped dramatically. The count of charged particles coming from inside the solar system. Particles the sun had been throwing past Voyager its whole life, suddenly plummeted, nearly to nothing. At the same time, the count of cosmic rays coming from interstellar space, from outside, shot upward to the highest levels ever recorded. Particles from home were draining away. Particles from the galaxy were flooding in. To anyone reading the map, this looked like the moment. This looked exactly like crossing the edge. The inside emptying out, the outside pouring in. Surely Voyager had finally left the solar system. The team almost said so. And then they checked the one reading the map said, had to change at the true boundary, the direction of the magnetic field. It hadn't changed. The compass was still pointing the same way it had inside the bubble. According to everything the scientists believed, you could not have left the solar system if the magnetic field hadn't turned. So they held their breath and held their announcement. Whatever Voyager had entered, it wasn't quite interstellar space. Not yet. It was something new, something the map didn't contain at all. They called it the magnetic highway. A region just inside the final boundary, where the sun's magnetic field had become connected to the galaxy's field beyond, so that charged particles could stream along these connected lines like cars merging onto an open freeway. The particles from inside raced out along the highway. The cosmic rays from outside raced in along the same lanes. But the field itself, the orientation of the road, was still anchored to the Sunday Voyager, was in a borderland, a place that belonged to both worlds and neither. This was a region no model had predicted. The scientists were, in real time, discovering and naming a feature of our own solar system that they were the first beings ever to encounter. The careful map had no magnetic highway on it. Reality had drawn one anyway. And the fact that the magnetic field hadn't turned. That became the central drama of the entire crossing. Because the team was waiting, patiently, certain, for the compass to finally swing and confirm the edge. They had been told their whole careers that it would. It never did. And the failure of that single prediction would become one of the most important and puzzling discoveries Voyager ever made. But before we get to that, Voyager finally, truly crossed, and it announced the crossing not with a magnetic turn, but with a sound. Voyager told us it had left the solar system not by what it saw, but by what it heard. Remember the broken instrument, the one that should have measured the density of the gas around the spacecraft directly, and that had failed back in 1980. Without it, the team couldn't simply read off the moment of crossing. They had to listen instead, using the instrument that detects vibrations in the gas, and wait for the sun to ring the space around Voyager like a bell. In the spring of 2013, it happened. A large eruption on the sun, many months earlier, finally sent its shockwave rolling all the way out to Voyager. And when it hit the gas surrounding the spacecraft, that gas began to oscillate, to vibrate at a specific pitch. Voyager's antenna caught the vibration, and when scientists turned that data into sound, They could actually hear it, a rising, eerie tone, the literal song of the gas at the edge of the solar system, the sound of interstellar space. The pitch of that tone told them the one thing they needed. A higher pitch means denser gas, and the pitch they heard was high, corresponding to a density about 40 times greater than anything inside the sun's bubble. That dense, cold gas could only be one thing: the interstellar medium, the stuff between the stars. There was no longer any doubt. Voyager was outside, and by tracing the data backward, the team could pin the exact moment the density had jumped: August 25th, 2012. The spacecraft had crossed the heliopause, the true outer skin of the solar system, and entered the galaxy. Let the scale of this settle over you. For the first time in the entire 4.5 billion year history of the Earth, an object made by living beings from this planet had left the bubble of our sun and touched the space between the stars. Every other thing our species had ever built or sent or dreamed had spent its whole existence inside the warm cocoon of the solar wind. Voyager was the first to step outside. A machine assembled by human hands in the 1,970 seconds, with less memory than a greeting card, became the first emissary of life on Earth into interstellar space. It had taken 35 years of unbroken flight. It had crossed more than 18 billion kilometers, and it carried, bolted to its side, a golden record of whale song and human laughter, and Chuck Berry, now officially adrift among the stars. But even in this moment of pure triumph, the puzzle remained. Voyager had crossed. The density had jumped. The galaxy was confirmed. And yet the magnetic field, the compass that the entire field of space physics had promised would swing at this exact boundary, still had not turned. The greatest milestone in the history of exploration came wrapped around the single most stubborn mystery of the whole mission. And that mystery is where the map didn't just bend. It broke. Here is the single most important way the map was wrong. Of everything Voyager discovered at the edge, this is the one that scientists still cannot fully explain. More than a decade later, the prediction could not have been clearer. Inside the heliosphere, the magnetic field belongs to the Sunday outside. In interstellar space, the magnetic field belongs to the galaxy, a field built up over billions of years by the churning of the entire Milky Way, pointing in its own direction, utterly indifferent to our small star. These two fields are not aligned. They point different ways. So when Voyager crossed from one realm into the other, the direction of the magnetic field around it absolutely had to change. The compass had to swing to a new heading. This was not a fringe idea. It was the textbook signature of the boundary. The thing every scientist expected. The final proof they had all been waiting for. Voyager crossed. The density jumped 40-fold. Every other sign confirmed it was in interstellar space. And the magnetic field pointed in almost exactly the same direction as before. The compass didn't swing. It barely twitched. Voyager passed from the sun's domain into the galaxies, and the magnetic field on the far side was aligned, improbably, with the field on the near side. It was as if you walked out of your house expecting to find a different world and found the furniture arranged exactly as it was inside. The one measurement that was supposed to define the crossing simply refused to behave. This broke something fundamental. If the galaxy's magnetic field near our solar system points the same way as the sun's field at the boundary, then either we have badly misunderstood the magnetic field of interstellar space, or the heliosphere is doing something to that field we never accounted for, draping it, combing it, forcing the galactic field to line up against the outside of our bubble like hair pressed flat against a head. Scientists have proposed model after model to explain it. The interstellar field, it seems, is being shaped by the very bubble it is pressing against, in a feedback no simple map had room for. When Voyager 2 crossed the boundary 6 years later, in a completely different part of the sky, scientists watched the magnetic field with held breath, wondering if its twin would finally see the predicted turn. it found the same thing. The field on the outside, once again, was aligned with the field on the inside. 2 spacecraft, 2 crossings, 2 different directions in space, and the same impossible result. This is what it truly means to say the map was wrong. Not that a number was off, the fundamental, confident, textbook understanding of how our solar system meets the galaxy was incomplete in a way we are still scrambling to repair. Voyager didn't just fill in a blank on the map. It proved that part of the map had been drawn from a misunderstanding, and it sent us back to redraw the boundary of our own home from scratch. And then Voyager 2, with one instrument its twin had lost, crossed the edge and revealed something its sister never could. When Voyager 2 crossed the edge in November 2018, it carried a working instrument that Voyager 1 had lost decades earlier, and it used it to measure the boundary of the solar system directly. For the first and only time in history, Voyager 1, you'll remember, lost the instrument that measures the gas directly back in 1980. It had to infer the Great Crossing indirectly by listening for the ring of the sun's shockwaves, but Voyager 2's equivalent instrument still worked. So when the second twin approached the heliopause, it could feel the gas around it in real time, measure its temperature, its density, its motion, second by second, as it passed through the most distant boundary humanity has ever touched. What it found was, once again, not what the map predicted. The boundary was sharper than expected. A remarkably thin, distinct skin between the sun's domain and the galaxy's crossed in a matter of a day, far cleaner than the gradual, fuzzy transition many had imagined. On the inside, the warm, thin solar wind. On the outside, the cold, dense interstellar gas. And between them, a boundary so crisp it surprised the people who had spent their lives modeling it. But Voyager 2 also found that the edge leaks. Just before it crossed, the spacecraft detected interstellar particles sneaking inward across the boundary into the sun's territory where they shouldn't have been. And just after it crossed, it detected particles from inside the heliosphere leaking outward into the galaxy. The wall of our solar system, it turns out, is not perfectly sealed. Material seeps both ways through it, blurring the very idea of a clean inside and outside. And then there was the heat. Just beyond the boundary, Voyager 2 measured the interstellar gas and found it hotter than the models had predicted. A region of unexpectedly warm plasma pressed up against the outside of our bubble. Decades earlier, theorists had predicted that a kind of pile-up should form at the edge, where incoming interstellar material slows and stacks up against the heliosphere, like a snowdrift against a wall. Voyager's measurements supported the idea that the boundary of the solar system is rimmed by exactly this kind of pile-up. A hot, compressed frontier where 2 great oceans of gas meet and press against each other. 2 spacecraft. 2 crossings, 6 years and billions of kilometers apart, in 2 completely different directions. And between them, they revealed an edge that was lopsided, breathing, foaming with magnetic bubbles, leaking in both directions, rimmed with unexpected heat, and bounded by a magnetic field that broke the central prediction of the entire science. Every confident line on the old map had been redrawn or erased. In the entire history of our species, only 5 machines have ever been set on a path to leave the solar system. And only one of them is still sending word back from the dark. Sit with that number for a moment. We have launched thousands of satellites, dozens of deep space probes, rovers and landers, and orbiters beyond counting. But of everything humanity has ever built, only 5 objects are moving fast enough to escape the sun's grip forever and coast out among the stars. The first 2 were the Pioneers, launched in the early 1970 seconds. The trailblazers that flew through the asteroid belt and past Jupiter to prove the path could be survived at all. Then came the 2 Voyagers in 1977. And then, decades later, a single newcomer, the New Horizons probe, launched in 2006, which flew past Pluto and is now trailing far behind, still many years from the edge the Voyagers have already crossed. 5 machines. That is the entire fleet of human emissaries to interstellar space, and 3 of them have already gone silent. The pioneers, our brave first scouts, ran out of power and faded from contact years ago. They are still out there, still coasting through the dark, but mute now, drifting forever with no one listening and no way to ever call them back. New Horizons still speaks, but it is far too close to home, nowhere near the boundary. That leaves the Voyagers. Of the only 5 things we have ever sent to leave the solar system, the twins are the only 2 that have actually crossed into interstellar space, and the only ones still alive enough to tell us what it is like out there. Every measurement we possess of the true space between the stars, taken from inside it, comes from these 2 aging machines and nothing else. When they fall silent, that window slams shut, and it may stay shut for decades until some future mission finally follows them out. There is no replacement waiting, there is no backup on the way. It makes the loneliness of the Voyagers almost unbearable to contemplate. Not only are they the most distant objects we have ever made, they are very nearly the only ones out there at all, and soon they will be the only ones still speaking. And then, before much longer, they will not be speaking either. But even Voyager wasn't finished. Crossing the heliopause was supposed to be the end of the story. The edge of the solar system reached at last. Instead, the spacecraft revealed a humbling truth that almost nobody outside of science fully appreciates. The heliopause isn't really the edge at all. The true boundary of our solar system lies thousands of times farther out. And Voyager, after a 45-year journey, has barely begun. Here is the fact that humbles everyone who hears it for the first time. Voyager left the solar system in 2012, and it is still, right now, thousands of years away from the real edge of the solar system. Both statements are true. It depends on what you mean by edge. The heliopause that Voyager crossed is the edge of the sun's wind, the boundary of the heliosphere, the place where the solar wind finally stops. That is a real and meaningful border, and crossing it was a genuine historic first. But the sun's wind is not the only thing the sun reaches out with. There is also the sun's gravity, and the sun's gravity reaches almost unimaginably farther than its wind. Far beyond the heliopause, far beyond anything Voyager has touched, there is a colossal shell of frozen worlds wrapped around the entire solar system. The Oort cloud. It is a vast spherical swarm of icy bodies, comets in deep storage, left over from the birth of the planets and flung out to enormous distances long ago. They are still bound to the Sunday. They still orbit it, slowly, in the deep cold and dark. And they are the source of the long-period comets that occasionally fall all the way back into the inner solar system and blaze across our skies. The scale of the Oort cloud is almost impossible to hold in your mind. Voyager is currently around 160 times the Earth-Sun distance from home. The inner edge of the Oort cloud is thought to begin at perhaps 1,000 to 2,000 times the Earth-Sun distance, and the cloud may extend outward to 100,000 times that distance, a meaningful fraction of the way to the next star. So how long until Voyager reaches it? At its current speed, and remember, this is the fastest object our species has ever launched. Voyager will take roughly 300 years just to reach the inner edge of the Oort cloud. And then it will take something like 30,000 years to pass all the way through it and out the other side. 30,000 years. To cross just the outer shell of our own solar system. The crossing the whole world celebrated in 2012, the leaving of home. That was Voyager stepping over the doorstep. The yard still stretches out for tens of thousands of years in every direction. This is the final, largest way the map deceives us. The neat little diagram of the solar system, with the sun and 8 planets, and maybe Pluto out at the edge. The real solar system, measured by where the sun's gravity actually holds sway, is so vast that our fastest emissary, after nearly half a century of flight, has covered only the first tiny fraction of the way to its true outer wall. And out there, in that immense dark, between the doorstep and the distant cloud, Voyager is not flying through nothing. It's flying through something, and it can hear it. Interstellar space was supposed to be empty and silent. Voyager found that it hums. After the spacecraft crossed into the galaxy, scientists kept listening with the instrument that detects vibrations in the surrounding gas, the same one that had revealed the crossing by catching the ring of solar shockwaves. At first, they assumed it would only hear something on the rare occasions when an eruption from the sun sent a wave all the way out to rattle the gas. The rest of the time, they expected silence. Instead, in data studied around 2021, they found a faint, steady, never-ending tone, a low, monotonous hum, always there in the background, coming not from the sun at all, but from the interstellar gas itself. The medium between the stars is gently, constantly vibrating, and Voyager, drifting through it, can feel that perpetual tremor like a swimmer feeling the faintest current. This changed the picture yet again. The space between the stars was supposed to be a calm, inert void, disturbed only by the occasional violence of our own Sunday. The hum revealed something else. A medium that is always active, always trembling with its own faint energy. Alive, in a way no one had assumed. And because the pitch of that hum depends on the density of the gas, Voyager can now use it as a continuous gauge, reading the density of interstellar space as it travels, instead of waiting for the rare gift of a solar shockwave. What that continuous reading showed was, fittingly, one more surprise. As Voyager moves deeper into interstellar space, the density of the gas around it is slowly rising. The deeper it goes, the thicker the medium becomes. Why? No one is entirely sure. It may be that the gas piles up against the outside of the heliosphere, denser near the boundary we just crossed. It may be structure in the local interstellar cloud that we never knew was there. The spacecraft is, right now, mapping a region of our galaxy that no instrument had ever sampled from the inside. And the map it is sending back is, once again, not the one we expected. This is the quiet wonder of where Voyager is now. It is no longer exploring our sun's domain at all. It is the first probe of the true interstellar medium, the actual stuff that fills the galaxy between the stars, sampling it directly, in person, and radioing the results home across the dark. Every day it survives, it sends back the first ever readings of a place humanity had only ever theorized about. But every day it survives is the heart of the matter now. Because Voyager is dying, its nuclear heart is fading, watt by watt, year by year. And yet physics was not the first thing that nearly ended this mission. Long before the power began to run low, Voyager faced an enemy far more familiar and far more human. Voyager was very nearly killed many times, and almost never by space. The thing that kept trying to end the mission was us. Remember how it began. Officially, this was a 4-year flight to Jupiter and Saturn. That was all that was funded, all that was promised, all that anyone in a budget meeting had ever agreed to pay for. Everything beyond Saturn, the flyby of Uranus, the encounter with Neptune, the entire journey to the edge of the solar system that we now consider the very heart of the Voyager story, none of it was guaranteed. All of it had to be fought for, again and again, in offices back on Earth, by people making the case that 2 still healthy spacecraft already flying through the outer solar system were worth the relatively small cost of keeping the lights on. And over the decades, that case had to be made over and over. Budgets tightened, priorities shifted. Newer, flashier missions competed for the same shrinking pool of money. More than once, the modest annual cost of operating the Voyagers landed on a list of things that might be cut to save funds. And more than once, the mission survived only because someone fought to keep it alive. The team running it shrank from a small army to a tiny crew, A handful of people guarding two of the most precious objects our species has ever launched, often working with a fraction of the resources the mission deserved. There is a strange and very human irony buried in this. We built a machine capable of surviving the radiation belts of Jupiter, the deep cold of interstellar space, the slow failure of its own components, and the passage of half a century. We engineered it to defeat almost everything the universe could throw at it. And the thing that came closest, again and again, to ending its journey was not a cosmic ray or a dying battery or the crushing emptiness of the dark. It was a line item, a budget vote, the simple human temptation to stop paying attention to something far away and quiet and old. Each time, the mission was spared. Each extension bought a few more years, and those years brought the planets beyond Saturn, the crossing of the edge, the first readings ever taken from interstellar space, discoveries that not a single person in those early budget meetings could possibly have imagined, won only because the mission kept stubbornly refusing to die. That was the long fight to keep Voyager alive against ourselves. The fight to keep it alive against physics is harder still, and it is happening right now. Right now, a small team of engineers is fighting to keep two dying spacecraft alive across the largest distance any humans have ever managed anything. And they are losing, very slowly, on purpose. The problem is power. Voyager's nuclear power source produces about 4 fewer watts of electricity every year as its plutonium decays. This is not a malfunction, it's physics, as relentless and predictable as the tide. When Voyager launched, it had enough power to run all of its instruments at once, plus heaters to keep everything warm, plus every system on board. Today, decades later, there is not nearly enough to go around. And so the team has been forced into an agonizing, years-long triage, deciding piece by piece what lives and what dies. One by one, they have switched off instruments, cameras, long ago, heaters that kept sensitive electronics warm, systems that once seemed essential. Each shutdown is a small death, a capability the spacecraft will never have again, traded away to keep the most precious instruments. The ones still sending back first-ever data from interstellar space, running a little longer. And here is the astonishing part. Again and again, the hardware has refused to die on schedule. When engineers turned off the heater for one of the science instruments, expecting it would soon stop working in the brutal cold of interstellar space, the instrument kept running, at a temperature far below the coldest it was ever designed or tested to endure. This is 1,970 seconds, technology operating in conditions its own builders would have called impossible, surviving on stubbornness and over-engineering and the careful devotion of the people on the ground. Those people are themselves part of the miracle. The engineers who built Voyager are mostly retired or gone. The code is written in computer languages almost no one learns anymore. To make a change, today's team digs through decades-old paper documentation, sometimes calling former engineers out of retirement to ask how a system was meant to behave. They are maintaining a machine older than they are, fluent in a dead dialect of computing, talking to it across 24 billion kilometers of vacuum. The goal is no longer discovery for its own sake, it is endurance. Every instrument they can keep alive, every year they can stretch the power budget, means more first-ever measurements of the interstellar medium, readings we cannot get any other way, and will not be able to get again for decades until some future mission finally follows Voyager out into the dark. So they ration the watts, they shut off another system, they buy another year, and occasionally, against all odds, they don't just keep the spacecraft alive, they reach across the entire solar system and bring a piece of it back from the dead, which is exactly what happened in one of the most extraordinary repair jobs in the history of engineering. In late 2023, Voyager 1 started speaking gibberish, and a team on Earth fixed it from 15 billion miles away. It began without warning. One day, the data coming back from Voyager 1 stopped making sense. Instead of the orderly stream of science and status information the spacecraft had sent home for 46 years, there was now a meaningless, repeating pattern. The same useless sequence over and over. The spacecraft was alive. Its heart was still beating, its signal still arriving. But it had, in effect, lost the ability to tell us anything. It was like a beloved relative suffering a stroke, still there, still breathing, but no longer able to speak. The engineers began the slowest, strangest detective story imaginable. Every question they asked, the spacecraft took a day and a half to answer. More than 22 hours for a command to crawl out to Voyager at the speed of light, and more than 22 hours for any response to crawl back. A single round of "try this and tell me what happened" consumed nearly 2 days. There would be no quick experiments, no rapid trial and error. Every move had to be reasoned out in advance, because every move cost almost 2 days of waiting in the dark. Patiently, command by command, over weeks, they traced the problem to its source. A single chip had failed inside one of Voyager's computers, a tiny piece of memory holding a fraction of the spacecraft's software, including some of the very code that packaged data for the trip home. About 3% of the memory was gone, and with it, the spacecraft's ability to communicate intelligibly. The chip could not be replaced. There are no repair missions to interstellar space. Whatever fix existed had to be made entirely in software, written on Earth and beamed across the void into a crippled 50-year-old computer. So the engineers did something audacious. They couldn't restore the dead chip, so they rewrote the affected code to live somewhere else. But no single open space in Voyager's tiny memory was large enough to hold it. So they broke the code into pieces, tucked each piece into a different, unused corner of the spacecraft's brain, and carefully stitched them together so they would all still work as one. Then they sent the first piece of the fix out into the dark and waited the day and a half to learn whether it had worked. In April 2024, the answer came back. Voyager 1 was speaking clearly again. The repackaged code held. Within weeks, the spacecraft was once more sending real science home from beyond the solar system, resurrected by people who had reached across 15 billion miles to perform surgery on a patient they will never see, running on a computer designed before most of them were born. It was not the first time the team had pulled off the impossible. Years earlier, when Voyager 1's main thrusters were wearing out, engineers fired up a backup set of thrusters that had not been used since 1980, and they roared back to life on the first try, as if they had been waiting all along. This is the strange devotion at the center of the Voyager story. A machine that should have died decades ago, kept breathing by the cleverness and stubbornness of people on a planet receding into the distance behind it. But there is one thing even their devotion cannot overcome: the simple, faint, fading whisper of the signal itself. The signal Voyager sends home is so unbelievably faint that catching it is its own miracle, and it gets fainter every single day. Consider what that signal has to do. It leaves Voyager's antenna with the power of a refrigerator light bulb. About 20 watts. 20 watts to bridge a gap of more than 24 billion kilometers. By the time that signal spreads across all that distance and finally washes over the Earth, its strength has dwindled to almost nothing. The power we actually receive from Voyager is less than a billionth of a watt. It is one of the faintest signals human beings have ever deliberately detected. A whisper from a machine so far away that its voice has been thinned almost to silence by the sheer scale of the journey. To put that number in human terms, the signal your phone pulls from a cell tower is trillions upon trillions of times stronger than the whisper we strain to hear from Voyager. The spacecraft's entire voice, by the time it washes over the Earth, carries less power than a single snowflake delivers when it lands on the ground. And out of that almost nothing, the engineers still reconstruct clean, usable data. Temperatures, magnetic readings, the density of interstellar space, carried home across 24 billion kilometers by a transmitter weaker than a refrigerator bulb. To hear something that faint, we built enormous ears. The Deep Space Network is a set of giant radio antennas spread around the Earth, the largest of them stretching 70 meters across. Dishes the size of a city block tilted up at the sky, straining to catch Voyager's vanishing murmur. The spacecraft is so far away, and the Earth turns. So we need these great dishes positioned around the planet to keep one of them always facing the right part of the sky. And there is a beautiful, poignant detail in this. Voyager 2, when it left, dove downward, below the plane of the planets, heading south. Because of the direction it went, there is now only one antenna on the entire Earth powerful enough and positioned correctly to send commands to it. A single 70-meter dish in the southern hemisphere, in Australia. One dish, on one continent, is humanity's only voice to one of its two most distant children. If that antenna goes down, we can still listen to Voyager 2, but we cannot speak to it at all. Every year, the challenge grows. The signal weakens as the distance increases. The power on board fades. The margins shrink. The engineers tune their giant dishes more carefully, listen more patiently, work harder to pull a coherent message out of an ever thinner whisper from an ever greater dark. There is something almost unbearably moving in this picture. Out there, alone, colder and darker and farther than anything we have ever made, a small machine keeps calling home, keeps sending back its faint report from the frontier. And here, on a warm blue planet, we keep building bigger ears and leaning in closer, refusing to stop listening. For now, the connection holds. The whisper still arrives. We can still hear Voyager, because the same fading power that forces the engineers to shut off instrument after instrument is leading, inevitably, to one final shutdown. Sometime in the next several years, Voyager will fall silent, and then it will keep flying mute for billions of years. The power keeps dropping by about 4 watts a year, and there is a floor below which the spacecraft simply cannot run even a single instrument, cannot keep its transmitter warm enough to call home, cannot do anything but drift. The engineers are stretching the time remaining with every trick they have, shutting down systems, rationing every watt. But they are buying years, not decades. Within the coming years, the last instruments will go dark. Sometime after that, the last signal will arrive. The faint whisper will finally fade below even the reach of our giant dishes, and Voyager will stop speaking to us. There will be no dramatic ending, no explosion, no crash, no final image. Just a last transmission that no one will know at the time is the last, and then a silence that does not end. We will lose contact with the most distant things our species has ever built, and we will never regain it. No future technology will let us call them back. They will simply be too far, too quiet, too cold. The conversation that began in 1977 will close, one-sided, into the dark. And here is the part that turns grief into something stranger and larger. Losing the signal is not the end of Voyager. It is only the end of our knowing about Voyager. The spacecraft itself will fly on. With no air to slow it and almost nothing to strike, it will coast through interstellar space at the same tremendous speed, carrying its golden record, essentially, forever. The silence is ours, not its. We go deaf. Voyager keeps traveling. Think about what that means across the spans of time ahead. Voyager will still be flying when every person alive today is gone. It will still be flying when the languages we speak have been forgotten and replaced. It will still be flying when the civilizations of our era are ancient history, then legend, then nothing remembered at all. The machine will outlast the memory of the people who made it, coasting silently through the galaxy with its cargo of whale song and human laughter, long after there is anyone left who knows it is out there. We tend to think of the silence as a loss, and it is. But it is also a kind of release. Voyager will stop being a spacecraft we operate and become something else. A relic in flight, an artifact of a species a sealed bottle still drifting on a current that runs for 10,000 times longer than all of recorded history. The mission will end. The journey will not. And the journey leads somewhere. Slowly, across spans of time that dwarf our entire existence, toward the stars themselves. In about 40,000 years, Voyager will drift close to another star. By then, it may be the only proof that we ever existed. Neither Voyager is aimed at a star. They were sent to explore our own planets, not to reach another sun, and the distances between stars are so vast that close is a relative word. But trace their paths forward through the deep future, and you find quiet appointments waiting. In roughly 40,000 years, Voyager 1 will pass within a couple of light years of a faint star in the northern sky. Around the same span of time, Voyager 2 will drift near a different one. They will not stop, will not orbit, will not be caught, just pass, silently, in the long dark, 2 specks of 1,970 seconds metal, greeting other suns across spans of time we can barely conceive, and then they will keep going. Once free of our sun's grip, the Voyagers will fall into orbit around the center of the Milky Way itself, circling the galaxy along with the sun and the stars for hundreds of millions of years, for billions. There is nothing out there to stop them. They will simply continue, around and around the galactic center, 2 of the most durable objects our species ever made. How durable? Consider the golden record, sealed in its aluminum cover, exposed only to the near-perfect emptiness of interstellar space. It could survive, readable, intact, the human heartbeat and the child's laughter still encoded in its grooves, for 1 billion years or more. That is a span of time that defeats the imagination. 1 billion years ago, there was no complex life on Earth at all. Nothing but microbes in the sea. Project the same span forward, and the record could still be flying, still legible, when our own world is unrecognizable. 1 billion years is long enough for continents to form and drown, for oceans to open and close, for whole branches of life to rise and vanish. The mountains you know will be worn flat. The constellations overhead will have drifted into shapes no human eye has ever seen, and through all of it, in the silence beyond the sun, 2 golden records could still be turning slowly through the dark, carrying a child's laughter, a Peruvian wedding song, and the sound of rain falling on Earth, perfectly preserved, waiting. Because here is the truth that places the whole journey in its final perspective. In about 5 billion years, our sun will swell into a red giant, and in its death throes it will scorch and very likely swallow the inner planets. The Earth as we know it, every mountain, every ocean, every trace of every life that ever lived here, the pale blue dot itself, will be gone, erased by the star that made it. And on that day, the Voyagers will almost certainly still be out there, coasting through the galaxy, untouched, carrying their golden records. Let that settle. The spacecraft may outlive the planet that built them. Long after the Earth is gone, 2 small machines and 2 golden records could still be flying through the Milky Way. The last surviving evidence that, on a blue world that no longer exists, there was once a species that looked up, wondered what lay beyond, and built something to go and find out. Voyager is not just an explorer. It is, potentially, our fossil, our epitaph, the longest-lasting thing we will ever make. And the people who built it understood, even at the start, that they were doing something that would outlast them. None more so than the man who waited 50 years for it. One person was there for the entire story, from before the spacecraft existed to beyond the edge of the solar system. And his patience may be the most human thing in this entire journey. Ed Stone became the chief scientist of the Voyager mission in 1972, 5 years before the spacecraft even launched. He was there for the frantic building, the once-in-176 years gamble, the twin launches in 1977. He was there for Jupiter, and the volcano on Io, for the rings of Saturn and the fateful choice at Titan. He was there for the lonely outer worlds, for Uranus on its side and the backward moon Triton with its impossible geysers. He was there for the pale blue dot. He was there, decades in, when the spacecraft hit the termination shock in the wrong place, when the magnetic foam appeared, when the compass refused to turn. He was there in 2012, an old man by then, when the density jumped 40-fold, and Voyager became the first thing from Earth to touch interstellar space. He held that job for half a century, 50 years on a single mission. A span so long that he guided the spacecraft from the dawn of the space age to the edge of the galaxy. Across nearly his entire adult life, he saw the whole map get redrawn, feature by feature, by the very machine he had helped send out to test it. He became, in a sense, the human memory of the journey, the one continuous mind that held the entire 45-year arc. He stepped down at last in his late 80s, and he died in 2024, having lived to see both Voyagers cross into interstellar space, having lived to see the thing the whole mission had been racing towards since before it began. He spent 50 years waiting for a machine to reach a place no one had ever been, knowing all along that the discoveries he cared about most might arrive only near the very end of his life, or after it. And they came, and he was there. He often said that every single day with Voyager was a day of discovery, and he meant it almost literally. For 50 years, some new piece of the outer solar system arrived on his desk, and he was the one constant who had seen all of it, from the first blurry images of Jupiter to the long silence of interstellar space. When he died, the spacecraft he had guided were still flying, still sending their faint reports home. In a sense, his life and the mission had become the same length, and both had reached far, far further than anyone in 1972 would have dared to believe. There is a lesson in that patience that goes beyond one man. Voyager is a monument to the long view, to people willing to begin something they may never see finished, to careers measured against the lifetime of a spacecraft, to a species occasionally able to act on timescales longer than its own impatience. The golden record was built to last 1 billion years. The mission was run by people willing to give it 50. Both are acts of faith in the future. Bets placed by people who understood they were part of something larger and longer than themselves. And that, in the end, is what the whole journey has been trying to teach us. Not just about the edge of the solar system, but about how little we know, how wrong our maps can be, and how worth it the going is anyway. We sent a machine to the edge of the solar system to confirm what we already knew. Instead, it taught us that we did not know our own home at all. Every confident line on the map turned out to be wrong, or incomplete, or drawn from a misunderstanding. The edge was not a sphere. It was lopsided, dented, breathing in and out on the rhythm of the Sunday. The outer region was not smooth. It was a churning sea of magnetic foam, bubbles wider than the orbit of the Earth. The boundary was not where we said. The protons were not as hot as we said. The gas beyond was not as empty as we said. And the magnetic field, the one thing we were most certain would turn at the crossing, refused to turn at all, and broke a piece of our understanding that we are still trying to repair. We had a beautiful, detailed, confident map of the edge of everything we call home. And then we actually went there, and almost none of it was right. This is not a story about failure. It is the opposite. It is the story of how knowledge actually works, not as a finished map handed down and memorized, but as a fragile drawing we keep correcting every time reality lets us get close enough to look. The scientists who drew the wrong map were not foolish. They did the best that could be done from a distance. And then they did the bravest thing science can do. They let a machine go and check, and when the answers came back strange, they threw out the old map and started drawing a truer one. That willingness to be wrong, to be corrected, to be astonished, is the whole engine of how we come to understand anything. And look at what we sent to do the correcting. Not an army, not a weapon. 2 small machines, built with less memory than a greeting card, carrying gold records of music and laughter and a map back to a pale blue dot, launched by a species that had only just learned to leave its own planet. On a one-way journey into a dark it could barely imagine, we packed up the best of ourselves, whale song and bark and a mother's first words to her child, and we threw it as far as we could into the night, on the faint chance that the throw itself might mean something. It means this: somewhere out beyond the edge of the sun's wind, in the cold and the dark and the faint perpetual hum of interstellar space, 2 emissaries from Earth are still flying, still carrying their golden records, still calling home in a whisper that grows fainter every day. Soon, we will lose their voices, but they will fly on, past the silence, past the end of the mission, past the memory of everyone who built them, past, most likely, the lifetime of the Earth itself. 2 small proofs that we were here, that we looked up, that we were not content to trust the map and went to see for ourselves. The edge of the solar system was not where we drew it. The shape was not what we imagined. The map was, in almost every way that mattered, completely wrong. And that is the most wonderful thing Voyager ever taught us, that the map is never finished. That the universe is always stranger and larger than our best drawing of it, and that the only way to ever find out is to do exactly what 2 small machines from 1977 are still doing right now, in the dark, on our behalf. There is a reason this story grips us. Beyond the science, we are all, in our own small way, working from maps we were handed, of the world, of our lives, of what is possible and where the edges lie. And Voyager whispers the same thing across 24 billion kilometers that every honest explorer eventually learns. The map is a guess. A useful guess, a beautiful guess, the best one we could draw from where we happen to be standing. The only way to ever know what is truly out there is to go and look and be willing to throw the old map away the moment the truth turns out to be stranger and grander than anything you had drawn. The edge is never where you think it is. It never was.